Hello, welcome to Equity Education, and today we're going to be looking at gas and ideal gas calculations. Alright, so let's get started. So I'd like you to open up your booklet and we will begin. So 1 mole of any gas occupies 24 dm cubed at room temperature and pressure. So this means that I can calculate the volume of any gas by doing number of moles of that said gas times by 24, and this will give me a value in dm, let's make that bigger, dm cubed. Okay, so what is the volume of methane gas in 3 moles? Well, I'm sure you can work this out. So my moles is 3 times by 24 gives me 72 dm cubed. Okay, what is the number of moles of methane if the volume of gas is 72 centimeters cubed? Alright, a bit more detailed, so I'll give you a minute to do that. Okay, so first of all I'd have to rearrange this equation. So N of, what's methane? My methane, NCH4, over my volume in dm cubed over 24. It's in centimeters cubed, so I need to divide by 1000 and divide by 24, which gives me a value of 3.0 times 10 to the minus 3 moles of CH4. Okay, sure you managed to do that as well. Next question, what volume of gas is produced when 1.5 grams of calcium carbonate is heated? Right, well I'll give you the equation first, as you may not know it. This is a thermal decomposition equation, and when we have a group 2 metal, the metal carbonate, it will produce the metal oxide and CO2. It's solid because it's an ionic compound. This is also a solid, and this is my gas. So you need to work out your volume of CO2 gas given this mass of calcium carbonate. Okay, I'll give you a few minutes to do that because it's slightly more in depth. Okay, so you're aware that you probably need to work out your number of moles of calcium carbonate to begin with. So I'm given its mass, so 1.5. I need to calculate the MR of the calcium carbonate, which is 100.1, which gives me 0.015 moles of calcium carbonate. I now have to look at my molar ratio, so it's 1 to 1. So my number of moles of calcium carbonate is 1 to 1. Therefore, my number of moles of calcium carbonate is equal to 0.0150 moles. Now what do I need to do? Okay, I don't know why I've worked out my number of moles of calcium oxide, because I'm working out my number of moles of carbon dioxide. However, it's also, as we see from the equation, it's a 1 to 1 reaction, so I will have produced the same amount of moles of carbon dioxide. Helps if I do the right thing. Okay, so I've worked out my number of moles of carbon dioxide as 0.0150. I'm asked to calculate the volume, so my volume of CO2 will be my number of moles of CO2 times by 24, which is 0.0150 times by 24 gives me a value of 0.36 dm cubed. I'm asked for it in centimeters cubed, so I need to times by 1000. I'm just going to write over here because I've run out of space, which equals 360 centimeters cubed. Okay, so still pretty straightforward. Okay, so we'll move on to ideal gas equation now. So The ideal gas equation is used when conditions are not room temperature and pressure in general. That's just a general rule. But my ideal gas equation looks like this. So PV equals nRT. Go through the units. So pressure. So technically, my units are Pascal. My volume is measured in meters cubed, technically, but we'll come back to this. Mole is obviously mole. This is the gas constant, and its units are, you don't need to remember this, but its units are the amount of energy required to raise 1 mole by 1 Kelvin, and my T is my temperature, which is in Kelvin. Don't forget, to get Kelvin, I need to do centigrades plus 273, gives me my temperature in Kelvin. That's a plus. Right, so I'm just going to go back up to here. So when you're doing the ideal gas equation, you can use this combination of pressure and volume, Pascal and meters cubed. However, most questions give the pressure in kilopascals and the volume in dm cubed. Yeah, so you can use either set of these, pascals and meters cubed or kilopascals and dm cubed. I think it's easier to use kPa and dm cubed because we have been using dm cubed already. However, if we were going to convert our units from meters cubed, it would be dm cubed over 1000, and from centimeters cubed, it's 1000 times 1000, so 1, 2, 3, 4, 5 over a million. Okay, so this is how we can convert it if you need to. I would say that you should stick to kilopascals and dm cubed. However, it's your prerogative. Okay. So I want you to have a go working out this gas constant. So calculate the gas constant given a standard temperature of 273.14 K, a pressure of 101.32 kPa, and for 1 mole of gas, a volume of 22.414 dm cubed. Right, I'll give you 5 minutes to calculate this. So we're using the ideal gas equation now. Okay, so first I need to write down my equation, PV equals nRT. I need to rearrange it to make R the subject. So PV over NT. Given all the values I need, so my pressure is 101.32 times by my volume 22.41. Because it's in kilopascals and dm cubed, I can leave them as in these units. My number of moles of gas is 1 times by my temperature, which is already being converted into Kelvin to 273.14, gives me a value of 8.314 joules per Kelvin per mole. And unsurprisingly, this is the value of my gas constant. You don't need to remember this. It's given in most data booklets, but that's what it is, and we calculated it as well. Okay, so important is this RTP and STP. So RTP stands for room temperature and pressure, and it's usually quoted as 298 Kelvin and 1 atm. And 1 atm can also be written as 101 kilopascals. For standard temperature and pressure, we are given the value of 273 on 1 atm or 101 kilopascals. You don't need to remember it, but we might use it in some of our calculations later. Okay, so moving on. So Right, so some assumptions, and I'm not going to spend too long on these assumptions either. I will just tell you about them. So the ideal gas law assumes that an ideal gas is a theoretical gas. It is used in calculations. And some assumptions are made. These are: all molecules have random motion, and it's straight line random motion. All collisions are perfectly elastic. So that means no energy is lost when these gas molecules collide with each other. All molecules have negligible size. So the size of the molecules doesn't affect the volume of anything, the container, and what are we talking about? And there are no intermolecular forces between molecules. Okay, so these are some assumptions that mean we can use the ideal gas equation. I don't really want to go into much detail about these at the minute. You just need to know that these are some of the assumptions we make when we're using the ideal gas equation. Right, so we'll move on to the more important thing, which is the calculations. So, examples using the ideal gas equation. And I think you'll be able to do this on your own. So 5.6 grams of liquid nitrogen was added to a 5 decimeter cube volumetric flask, and the temperature was allowed to rise to 25 degrees Celsius. Calculate the pressure inside the volumetric flask. Well, give you a quick start. So PV equals nRT. So I need to use my my ideal gas equation. I don't have my number of moles, so maybe that's where you start off. Okay, back in a minute. Okay, so first of all I need to work out my number of moles of N2. So my number of moles of N2 is 5.6 divided by it's N2, so 14 plus 14 times 2 is 28. Gives me my number of moles, which is 0.2 moles. Okay, so I can start to calculate the pressure. Oh no, I can't, not yet, because first I need to convert my temperature into Kelvin. So 273 plus 25 gives me 298 Kelvin. Do I need to do anything else? My volume is in decimeters cubed, and I'm going to calculate in kPa, so no, I don't need to do anything else. Right, so I'm calculating the pressure. I know the volume, I know my number of moles, I know the gas constant, and I know my temperature. Okay, so I can rearrange this equation. So P equals nRT over V. My number of moles is 0.2. My gas constant is 8.314. My temperature is 298 Kelvin. My volume is 5. And this will give me my pressure, which this gives me a value of 99.1 kPa. Okay, easy. So all you are doing is substituting your values into the ideal gas equation. Okay, so we will move on. Well, 1.68 grams of a noble gas occupies a volume of 500 centimeters cubed at room temperature and pressure. Identify the noble gas. Okay, so I reckon you might be able to do this. Will you be able to do part of it, I think? So first of all, work out the number of moles, and then we will go through it together. Okay, so you need to look back at your room temperature and pressure first of all. Okay, so you should have a look back and found out that your room temperature and pressure, temperature is 298 Kelvin, pressure is 101 kPa. So the first thing I need to do is work out my number of moles using the ideal gas equation. So PV equals nRT, so N equals PV over RT. Right, so do I need to do anything else before I start? Yes, I do. So I need to convert my volume into decimeters cubed. So 500 divided by 1000 gives me 0.5 decimeters cubed. So now I have kilopascals and 0.5 and decimeters cubed. So I can now go back to my equation. So my pressure is 101 times by the volume 0.5 times by my gas constant 8.314 times by my temperature in Kelvin was 298. Okay, so that gives me a value of 0.0204 moles. Okay, so I know that I have 0.0204 moles of this noble gas occupying this volume at room temperature and pressure. So I need to identify this noble gas. So I can identify this noble gas by working out its MR. So 1.68 over 0.0204 gives me a value of 82.4 grams per mole, and it's not going to be exact. So we look for the noble gas which is closest to 82.4, which is krypton. Okay, so slight technical issue there, I'm back. So we'll go through the next one together as it's slightly more difficult. So if the volume of gas collected at 50 degrees Celsius, 110 kPa is 75 centimeters cubed, what would the volume be at RTP, 298 Kelvin and 101 kilopascals? Okay, so let's have a think about this one. So we know that from this question, the number of moles of gas, so N of gas, remains the same. So we can say that N, let's actually start with my ideal gas equation. So PV equals nRT. If I rearrange this, I can say that N is equal to PV over RT. So at the first temperature, first pressure and first volume, I can say that N is equal to P1 V1 RT1. So here's my temperature, pressure and volume. I can also say that at my second pressure, volume and temperature, that N is also equal to P2 V2 over RT2. So this N doesn't change. So N here is the same. So I can combine these two equations to come up with P1 V1 is equal to T1 V2 V2 T2, and I've removed the gas constant because it appears in both equations. Hope you're following so far. Right, so I've got a form of this ideal gas equation which I should be able to use to answer this question. First thing I need to do is to convert the units. So for P1, T1 and V1, my pressure is already in kilopascals. My temperature is in centigrade, so I need to convert it into Kelvin. So it equals 383 Kelvin. Excuse me, 323. Can't do any maths today. 323 Kelvin, and I also need to convert my volume into decimeters cubed. So 75 divided by 1000 equals 0.075 dm cubed. So I have my pascals, my pressure in kilopascals, my volume in decimeters cubed. Okay, my pressure in my second equation, or my second pressure, is already in kilopascals, and my temperature is in Kelvin already, and I'm going to calculate my V2, my volume. So I can put the values into this equation. So we know the pressure is in the first conditions is 110 times by 0.075 over my temperature, which is 323, which equals 101 times by my volume, which is V2, that's what I'm trying to work out, over my temperature, which is temperature is 298 Kelvin. Okay, so I've given you the equation and the values. I want to see if you can do the rest yourself. Okay, so I'll be back in a minute. Okay, so let's see how you got on. Right, so I'll simplify this side to begin with, the left hand side. So 110 times by 0.075 divided by 323 equals 0.0255 equals 101 times by V2 over 298. So I can multiply this side by 298, which gives me a value of 7.61 equals 101 times by V2. And now I can divide by 101, 7.61 divided by 101, which will give me my V2 volume. So I'm dividing here because it's times, which gives me a value of 0.0753 decimeters cubed. And I think in the question it asks us to convert into centimeters cubed. So 0.0753 times by 1000 gives me 75.3 centimeters cubed. So I have worked out my new volume under the different conditions of this gas. Okay, so we are done. As usual, hope that was useful, and I will see you again next time. Okay, bye bye.